Almost think like capillary tubes or like
So it had a bigger hot base and a smaller.
I'll give you guys some time at the end if you want to talk. Okay, here we go. Mr. Adam Gottlieb, University of California. Hey, physics is fun.
Alright guys, so the reason I was stalling is I'm videotaping myself, don't worry about that. So yeah, once again, my name is Adam Gottlieb. I'm going to be a senior at UC Berkeley, so that means I took this class in 09, 010, and this class, ADB, we took over 08, 09, sounds like forever ago.
We never took C mechanics.
Yeah, that's right, I took E&M, but I'm an engineering physics major, so what that means is basically a physics major, but I'm in the School of Engineering. So I have like engineering requirements, and humanity requirements, don't worry about it. Okay, what are we going to do today? So I'm going to introduce you guys to special relativity. So special relativity is something you can take a whole course on, literally, and I'm going to try to teach you guys in about 30 minutes. So I'm going to be skipping a lot, ask questions at any time. I'll go pretty slow, and I'll go pretty basic in relation to what you guys already know. I'm not going to try to use any notation or anything like that. So again, ask me questions if you have any, and hopefully you'll learn something like really cool, because relativity is really cool. Okay, so the rundown of what we're going to do. We're going to learn what Einstein's postulates were. They're going to seem really simple at first, but then they're going to make the whole world really confusing. You'll see what I mean by that. I'm going to introduce you guys to Galilean transformation. You guys know what that is, Galilean transformation? Kind of? Okay, we're going to watch a little video on simultaneity, and then we're going to take the Galilean transformation, which is basically classical mechanics, and make it into the Lorentz transformation, which is relativity. And then we're going to do a cool example, length contraction, and you'll see what that is when we get there. Okay, so again, ask me any questions at any time. I will stop, I have no problem. Okay, so let's start with what is special relativity. What do you guys know about special relativity? What have you heard? What are some things that you guys might have read or heard, anything that I saw your hand?
It has to do with like light and the speed of light.
Okay, speed of light.
Like it affects, like light speed is always the same no matter what your frame of reference is.
Okay, that's going to be up there for sure. All right. Anyone else have any ideas? What? Yes. Okay, that's a start. So it's special relativity has to do with inertial reference frames, which means that acceleration is 0. And general relativity has to do with accelerating reference frames. That's correct. All right, let's just get started. So what are Einstein's two postulates? I'm going to go word for word here. So Einstein, what did he say? His first postulate. This is going to seem pretty obvious. You guys can't read that, right? Okay. Okay. The laws of physics are the same in all inertial reference frames. So I mentioned this before, inertial reference frames means that acceleration is 0. So you're either standing still or velocity is constant, right? That seems so obvious. The laws of physics are the same in all inertial reference frames. So whether I'm here or somewhere else, moving, not moving, the laws of physics are the same everywhere. That should make complete sense. So then, I'm actually going to shorten this next one so I don't want to write too much. One of you guys mentioned this before. The speed of light is constant, and it equals the value of c, we'll call it. So this is one of the things that might not be so easy to accept right now. You can derive it using Maxwell equations if you guys have learned Maxwell equations, but this is mechanics, so I'm not getting into that and derive it from them. But basically, no matter how fast you're moving or what inertial reference frame you're in, you'll measure the speed of light as the same. Okay? And we know it as 3 times 10 to the 8 meters per second, and it's constant, and it doesn't matter what the source is moving towards you, away from you, it's always the same. But so far so good. Nothing's wrong yet. These can both coexist. But we're going to introduce something, another concept that'll change things up a bit.
Excuse me, can you comment on why the second postulate was something that we didn't?
You want me to get into like the ether and stuff like that, or do you want me to?
Just a brief, yeah, well, yeah.
Okay, so basically, some people didn't think that the speed of light might be a constant number. They thought that there might be this ether that, like a medium that light traveled through that we just can't detect right now. Kind of like how sound uses air, it's pressure waves. That's what sound is. So there was this experiment called the Michelson-Morley experiment, where basically, I'm not going to draw it and really explain it too much, but they sent light in one direction that the Earth was spinning. So they thought that if they sent light in that direction, it'd be a little bit faster than if they sent it into a perpendicular direction, because it had the extra velocity of the Earth rotating and moving throughout space. And they compared the two results, and they're exactly the same. So there was no ether. And they thought if you're moving with the ether, then you have a little extra velocity. If your light is shining perpendicular to the ether, then the velocity would be c as opposed to the extra velocity you got moving with the ether. They proved that there was no ether, which suggested that light travels independent of the media, which means that it'd be a constant number.
Thank you. The reason I asked, there was real evidence for this, that it was always the same no matter what the frame of reference, but people had trouble accepting it. Einstein said, let's just accept it and see where it leads us. Okay, that's a very scientific way of looking at nature. Just because it doesn't make sense to your preconceived notions, don't discard it, accept it, and see where it leads. That's how breakthroughs are made.
Thank you, Covert. Okay, so now we're going to go through the concept you guys are really familiar with, which is I guess I'll draw a little picture to describe to you guys. So we got a car, and we got Mr. Covert, and he's throwing a baseball. Let's say he's throwing the baseball at V2, and the car is moving at velocity V1. And let's see, we have someone else, my friend Josh over there, he's watching. So this basic concept is if Mr. Covert sees himself with the ball at velocity V2 in his reference frame, let's say there's no air resistance or anything like that, he sees the ball moving at V2. But Josh over here sees the car moving at V1 plus Mr. Covert throwing the ball at V2. So for Josh, he sees that V12, or the velocity that Josh sees, is equal to V1 plus V2. So Mr. Covert throws the ball at 10 meters per second, car is moving 20 meters per second, he'll see the ball move at 30. Make sense? Right? Okay. You guys are smart people. Alright. So what I'm going to do is I'm actually going to derive this using a different notation, and then we're going to see where that notation takes us and why it disagrees with Einstein's postulates. So I'm going to introduce what's called the Galilean transformation. So what transformations do is they tell you how coordinates transform from one reference frame to another. So I'm going to draw 2 reference frames right now. So let's call this the S reference frame. So this is the y-axis, this is the x-axis. Let's call this the S prime reference frame, which means that this is the y prime axis, this is the x prime axis. And what I'm going to do differently with the prime reference frame, I'm going to give it a velocity. Let's see, this I'm giving it v1. So we have 2 people who are making observations. One who's standing still, this is Josh, and someone else who's moving, so this would be Mr. Covert. So now we have to see how the coordinates transform from one reference frame to the other. So we have 4 coordinates. We have 3 time coordinates. We have x prime, y prime, z prime, and t prime. Okay, we're going to start with these 3 because they're the easiest. Y prime. Seeing that he's moving in the x direction, the y isn't affected at all. So when he measures in the y coordinate, he'll also measure y prime equals y. Same thing with z. Z prime equals z. Now we're doing Galilean transformation, so we're thinking classical mechanics. So we're thinking that time is universal. There's absolute time. There is 1 second, and 1 second is a second no matter what you're doing. So we're going to call t prime equals t. So now what do we do for x prime? So what we're doing is we're trying to find a way such that what he measures in the x direction, we can relate it back to what this person measures in the x direction. So that's not too straightforward, but I'd be pretty impressed if one of you could figure out what the formula would be for x prime. So we're looking for a way that what Mr. Covert measures in his x direction, and how to compare that to what Josh measured in his x direction. The ideas. They're not going to be the same because one of them is moving in the x direction, one of them is standing still. I'll give you a hint, there's 3 variables, x, v, and t. Alright, I'll give it to you guys, not that bad. So, x prime is x minus vt. The best way to think about this is, let's picture the origin. So, for Mr. Covert, he's observing from himself. He's always at x equals 0, or x prime equals 0. So, what Josh sees is actually Mr. Covert moving at a velocity v. So at any given time, he's vt away. You know, velocity is distance over time. Velocity times time is the distance he's moving. So the origin at x prime equals 0 will have to be vt less than x. That makes sense? Okay. So this is a Galilean transformation. All looks good, classical mechanics. Not too bad. So let's actually derive this using this guy. So what is velocity in general? I had mentioned it before, someone's given it to me. So. Right. So velocity is change in distance over time. Okay. So what I'm going to look now is the velocity that's measured, what this velocity is, I'm sorry. So we're going to call this v prime would equal change in x prime over change in t prime. So now we're just looking at Mr. Covert's reference frame. So just expanding this out, we plug it back into this formula. So change in x prime would be change in x minus v change in t over change in t prime, which we said was equal to t. Okay? So now we're going to do some algebra. So I'm going to move this change in x over this change in t, and I'm going to cross out this change in t. So we have, I'll just write it out, change in x over change in t minus v. You guys see how we got from there to there? This is a different, I'll explain which velocity this is, which velocity that is. So this velocity, change in x over change in t, is what we observed from Josh's reference frame. So we're going to call it v1, v2. Sorry, v1, 2, I called it. This velocity was the velocity of the moving reference frame, so we're going to call that v1, so minus v1. And v prime in the Galilean transformation is what Mr. Covert recognized, so he saw v2. So voila, move this guy to the other side, and we have this. v1, 2 equals v1 plus v2. So I just derived it using the transformation. So now this is fine, except when this happens. What if v2 is light? So what if instead of throwing a baseball, Mr. Covert shines a flashlight? Or he's in a car and he puts his headlights on. So now this is suggesting that what Josh would see, v12 equals c plus v2. So he's suggesting that Josh sees the speed of light, so this would be velocity of light equals c plus the velocity of the moving object. got a problem. Galilean transformation can't be right. So something's got to give. Maybe it's something with distance. Maybe it's something with time. So I said someone said something.
Yeah, it should be V1.
You're right. Yes. Good. Right. Good. Paying attention. So something's got to give. Not all of this could agree. So we're going to watch a little video to start get our minds thinking about what possibly could lead to this. Oh, there's sound.
Imagine two observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear, but her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct, within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
Alright, interesting. So now we have a new interpretation of what time is. So maybe time in someone's reference frame isn't the same as time in someone else's reference frame. So maybe time also transforms. So now I'm making an adjustment. I'm saying, this is what I want. I want my new transformation to have y prime equals y, because again there's no motion to y, z prime equals z. But I'm putting question marks next to x prime and y prime. Okay, so this is where I'm going to skip a lot of steps. So what is x prime? So maybe Einstein started with this idea, maybe not. But what I'm going to do is I'm going to start with my Galilean transformation. I'm going to say that it probably has something to do with Galilean transformation. There's something else there. I don't know what it is yet. So I'm going to call it gamma. I'm going to multiply gamma by my x minus vt. But I still don't know what t prime is. So starting from here, what's going to happen is a lot of algebra. I'm going to do some manipulations and mix and match things to make sure that the speed of light doesn't get violated. And I'm going to get the Lorentz transformation. So I'm going to skip right to it and give you guys the answer. So, x prime, as we said, is gamma x minus vt. Y prime equals y, z prime equals z, t prime equals, I want to get this wrong, gamma t minus dx over ct. Okay, so what is gamma? So clearly gamma must be some combination of x's, v's, t's, maybe some y's and z's. It's not. And maybe some primes. So what it ended up being is the way what gamma had to be to make this work for low limit and the high limit that our velocity is approaching c. Gamma is this, which you might have seen before. It's 1 over the square root of v minus c squared. So the Lorentz transformation, which is right here, is now our new transformation. That's what this is replaced with. So we're going to get rid of that right now.
Adam, that transformation, Lorentz is named after the person who discovered it.
Yeah,
developed it, right? That was something done prior to Einstein.
Yeah, so the Lorentz transformation was actually done by a mathematician with the last name Lorentz, and Einstein, I guess, used his result, and it matched up well with his ideas. That's true. So, let's see where. All right, so we have the Lorentz transformation, and we have gamma. So why don't we use this? Why does Mr. Covert teach you the Galilean transformation? Why don't we even worry about this? Let's look at gamma. So, when the velocity that the object is moving is very small compared to c, what number does gamma come close to? What does gamma approach? 1, right. So when v is much less than c, this is my notation for much less than, gamma is approximately 1. How'd you get there? Right, so v over c would be approximately 0. It's approximately 0. So when we look back at the Lorentz transformation, gamma equals 1, if you guys remember, that gives us our Galilean transformation. If v over c is approximately 0, this goes away, gamma equals 1, and we're back to our Galilean transformation. So this is why we don't notice it. And I want to be even more exact. What does gamma actually look like on a graph? So let's call this v, this velocity. Let's call this gamma. This is our value of 1. And let's say our velocity is approaching c. We know nothing gets past there, so I'm going to put a little dotted line there. What gamma actually looks like if you were to graph this function is something like this. So we live in this region, right here, where gamma is approximately 1. Only when the velocity is very close to c, a significant fraction of c, do we actually see this actually mattering. So when does it matter? Particle physics, high energy physics, you'll see a lot of things that approach the speed of light easily. Protons, electrons, they go to the speed of light all the time. So that's why it actually matters, and you see significant results.
Even with satellites, right? Even though it's a small fraction of c, it's still it's significant if you want to GPS.
Yes, correct. So the GPS system, I actually did my APC independent project on this. So if these satellites that are orbiting Earth have to go a little bit faster in order to stay geostationary, which means that if you want to hover over the United States and you're a satellite that's a couple thousand miles out in space, you have to move a little bit faster than Earth in order to stay over the same spot, which you guys should know. So because they're moving that little extra speed, every year they're offset by 7 seconds, our GPS systems. So they actually do have to account for relativity. So the clock in our GPSs will run 7 seconds slower each year. It doesn't seem like that much, but if your GPS, you're on one street, GPS tells you you're in New Jersey, then you got a problem.
That also accounts for general relativity too.
Yeah, so there's another effect of general relativity with satellites because they're in a smaller gravitational field. We're not getting to that. But that's also an effect. Okay, so now we have our Lorentz transformation, and we're going to do something cool with it. So I'm going to get rid of this pre-mess right here. And we're going to do something called length contraction. So one of the results of this Lorentz transformation is how we perceive length in different reference frames. So in terms of coordinates, the length of an object, let's say if the object is laying in the x direction, final minus initial, right? So let's call it x2 minus x1. Make sense? So the length in the prime frame that we had defined before would be the x2 position in the prime frame minus the x1 position in the prime frame. This is just where we make the measurement from the end of the object to the beginning of the object. So now what we're going to do is we're going to apply our Lorentz transformation to length. So L prime equals x2 prime. I'm going to plug in this formula. So this would be gamma x2 minus b time 2. I'll explain what time 2 is in a little bit. Minus gamma x1 minus b t1. Okay? Let's factor out the gamma and put everything else in the parentheses. So we have gamma x2 minus b t2 minus x1 minus minus plus b t1. So when we make a measurement on an object, we're assuming that in the frame we're in, we make that measurement at the same time. So if you want to measure someone's height, you see where their feet are, you see where their head is, and you take the difference. You don't measure where their feet is, have them walk around, go upstairs, go downstairs, go somewhere else, sit down, then you take a measurement of their height and say, okay, they're 3 feet tall. No. You take a measurement at the same exact time. So T1 actually will equal T2, and therefore these will cancel out each other. So what are we left with? Gamma x2 minus x1. x2 minus x1 is what we define as length in the stationary frame. So that equals gamma L. Written a little bit differently, I'm going to divide the gamma over and say that L equals L prime over gamma. So this is our formula for length contraction. So what this is saying is the length observed in the stationary frame is equal to the length observed in the moving frame divided by gamma. Now let's look at gamma again. What do we know about the limits of gamma? Is it sometimes a negative number? Sometimes a negative number, sometimes a positive, 0. What do we know about gamma and its actual numerical value? It's 1. Okay, someone say greater than 1? Yes, that's the right answer. It's always greater than 1. So this is going to be some fraction. We're taking this fraction, we're saying 1 minus some fraction. And when you take it over in the denominator, it's always going to be something greater than 1. Something like 2 or 5. No? But it can't be less than 1. So what this is saying is that if we're stationary, and we know that an object in the moving frame has a certain length, since this is greater than 1, this value, it's going to seem shorter to us. So when we're observing an object moving close to the speed of light, it's actually going to start shrinking as it moves. Interesting. It is interesting. So we're going to explore this. I'm going to give you guys an example, and we're going to talk about it, about this length contraction. So I'm going to start with a fresh board, and I'm going to put our formula up here for length contraction. Now this gets confusing because we're in 2 different reference frames, and I'm pretty comfortable thinking about 2 different reference frames. In case you guys aren't, I'm going to repeat what this means again. So L prime is the distance measured in the moving frame. So let's say Mr. Covert before was moving on a car. Well, let's say the car is moving really close to the speed of light. So when he's holding an object, let's say a pole, he measures the pole. That's a natural length of the pole, also known as the proper length. So he's stationary with the pole because he's holding it. He says it's, let's say, 10 meters. But someone else who's not Mr. Covert in a stationary frame, and Mr. Covert's moving, will see that 10-meter pole, something smaller than 10 meters. Make sense? Well, we just proved it theoretically with the Lorentz transformation. How we got these gammas is a bunch of basically algebra. There's a lot of different ways of doing it. If you guys know vector calculus, you can derive it with that. If you guys know tensor analysis, you can derive it with that. Obviously, I'm not going to introduce these things. But the Lorentz transformation, if you can accept this, if you can accept how we got from the Galilean transformation, it wasn't correct. We introduced a new factor, gamma. And then we did a bunch of algebra to produce that this is our new transformation. This is the mathematical result we get.
Reality is only an illusion.
And we do observe this. So, all right, now that we have our length contraction formula, let's work with an example. What's the time on this period?
This period ends in about another 5-6 minutes. You have whatever you need next period also.
Okay. So this is a paradox that was initially proposed to me by Mr. Covert when I was in his class. I think you call it the bus in the garage.
The bus in the garage, yeah.
I'm going to do a pole in the barn just because.
You gotta put your own twist on things. It's okay.
I guess so. So pole in the barn paradox. Or not so paradox. Okay. So this is the picture I'm going to draw. Here is, let's call him Mr. Knapp. Not drawn to scale. Okay. Mr. Nappy sees a barn. Barn has length, let's call it L barn. The pole that Mr. Nappy is holding has length L pole. And you guys have Mr. Chernick?
Oh, yes.
All right, this is Mr. Chernick. Mr. Nappy sits through my lecture, and he says, I learned something about length contraction. I have this pole, and let's say length of the pole is bigger than length of the barn. So I have this big pole, Mr. Nappy, and I know that if someone's watching me run really, really close to the speed of light, the length of my pole is going to shrink. And I bet you, if I run fast enough, I can shrink my pole so it fits into the barn. Now, Mr. Chernick also listens to my lecture, and he says, oh, that's interesting, but I think that when Mr. Nappy runs into the barn, what he's going to see is the barn coming at him at a really fast speed, and therefore the barn is going to shrink. And then we have an even smaller barn with a large pole. How are we going to get the pole to the barn? So they make a bet. Mr. Nappy says, I know something about relativity. I'm going to bet you some money that I can get this pole into the barn. Mr. Chernick says, okay, well, I'm going to take the bet. And I bet that you can't fit that entire pole into the barn. All right, let's investigate and see who wins the bet. So I'm going to start by putting some numbers on it. Let's call the length of the pole 10 meters. Let's say the length of the barn is 5 meters. And let's say that Mr. Nappy decides to run at 0.866 c. So 87% of the speed of light, approximately 87% of the speed of light. It's really fast. So let's see what Mr. Chernick will observe. This is what Nappy thinks Chernick will observe. This is what he does. So let's go to our, let's see, Chernick. With our notation from before, Chernick will be the S frame. So not the prime frame. Okay, so we have our, what Chernick is observing is the pole. So we have our equation for length contraction. So length of the pole equal length of the pole in the prime frame divided by our factor gamma. Okay, so I'm going to put in what gamma equals here. So we have length of pole prime multiplied by, if you guys remember what gamma was, I actually erased it, but it was 1 over the square root of 1 minus b over c squared. So now we have the square root of 1 minus b over c squared. Okay, so let's plug in some numbers. Length of the pole in the prime frame. So that's going to be 10 meters, because as measured in the rest frame of the pole, which is moving, we measured the pole as 10 meters from before. So we have 10. I'm going to drop my units, like you guys shouldn't. Divided by, times the square root of 1 minus 0.866c over c squared. So I did this math already, and equals 5 meters. So Mr. Chernick will observe the pole as being 5 meters long. All right, what does Mr. Nappy see? So he's going to see the barn moving. So let's call length of the barn the length of the tracking forward for length of the barn. All right. Let me just get these numbers up here and then give you guys a question that you guys can take your break thinking about. So length of barn would be 5 times our gamma factor, 1 minus negative 0.866c over c squared, which equals 2.5 meters. So Mr. Nappy sees the barn as 2.5 meters, and he's holding a 10-meter pole. Mr. Chernick sees the pole as 5 meters with a 5-meter barn. So it seems like it'll fit in Mr. Chernick's reference frame, but it won't fit in Mr. Nappy's reference frame. So I'm going to give you guys the next, I guess, 3.5 minutes to think about who's going to win the bet and whether the pole will actually fit in the barn or not.
All right, so you guys got to, if anybody guys go grab lunch or do what you're going to do, think about it, come back, no worries. I know.
Right here. So gamma is 1 over the square root of 1 minus b over c squared. This is how p prime. So the reason the prime frame is 10 is because that's the rest frame of the pole is the moving frame. That's why it's 10.
Do you want to speak to the class?
Yeah.
Which ones?
So I'm actually not doing the I did entry the last 2 summers, so. Santa Barbara. He's leaving tomorrow, I'm leaving Sunday.
Are you not tomorrow?
Yeah.
I hope the family enjoyed seeing you for
Yeah, right.
a couple days.
You guys want to ask me questions too? I can ask them for thinking.
So this is what mechanics with some calculus in it.
Yeah, no, good.
I was watching some physics video or something. I don't remember what mechanics. And it was if you're in a car, you're driving forward and then you walk forward like a certain distance, like you're driving 50 miles an hour, you walk forward like 5 miles an hour. If you're not if you're looking at like the rubber train on the road, you're actually seeing a person walking at like 54.9 or 58 miles per hour or something like that.
Yeah, that's that velocity addition form that I was talking about before, which is what led us to creating the whole Lorentz transformation in the first place. Let's say you walk really close to the speed of light, right? So now you're adding those two numbers, and you can't combine them. There has to be something else. Something else there. And that's what the gamma factor was. So it does. It is in the same route. Yeah.
Now, like I understand, like when you're traveling at speed of like the light coming back to you like in a string state, but then with like something like a black hole, wouldn't the light be like elongated because force like special relativity?
You're saying a moving black hole should length be
No, like something like black hole goes into a black hole, it would be elongated.
Okay. So black hole physics is something very complicated. The idea of it is that when you approach a black hole, I don't know if you've ever watched videos on like YouTube channel or something, everything seems to slow down. So think of it as slowing down your velocity, and right as we just showed that when things are moving fast, they tend to shrink. This is like you're stopping. So you're almost like stopping time, and then you can have to see the opposite of that, but longer. That's the basic idea.
Something this way,
Going into a black hole after
You would to a light approach a black hole.
so it's just like L1, L2, L3.
That's in statics? It sounds
No, it's solid.
So one thing about this light is nothing with gas and then it goes to be like so photons, which is like they don't have mass.
That's so bad.
So it's you have to actually you have to prove that anything that goes to the light has force.
It has that like 10 minutes now. You can't run any.
Yes.
Before.
It's
Lazy at that time.
It's good. The sequence forwards. We'll give people just another
Okay, yeah.
couple minutes. You can stick around for when you have.
We're watching a movie.
You're here from what? Bio? AP Bio?
From environmental science.
Environmental systems. What happened to the other character that was with you?
They stay doing work.
Yep. Well, I don't remember. I'm supposed to remember what. I remember the experience.
Yes, they're weightless wave particles.
Yeah. Well, and that's where.
Well, yeah. So the experiment that showed me that our lab like comes in a package. It's also using one of the components of Einstein's but Einstein wasn't able to price for. So what's the experiment? Here's guys going to do any light photons hit the metal and they start current.
You say not required.
But like,
I'm sure you're gonna have to take classes.
Well, actually, yeah,
what it basically showed is that so you can take the force on frequency, like the energy of the light, but he showed what shine as much light as possible on the metal sheet. But if it didn't happen, then you need to pack it and have
You're back from
nothing
there.
happen. But once it's just packed and has enough energy, you can knock off an electron from the sheet. You want to get it's just like this happens. So it's kind of like you can throw as many functions into the wall as possible. It's not you need like a certain amount of energy in order to get that process going. So that suggests that there should be like package.
another one in there. Yeah.
So any of you, should I start?
Yeah, you know, yes.
Any of you guys have some initial ideas? Who's going to win the bet?
Thanks for the trip.
So Mr. Nappy thinks he's going to fit in the barn because he thinks Mr. Chernick will see this. Mr. Chernick thinks he's going to win the bet because he knows that Mr. Nappy will see this. Yeah.
I think that Mr. Chernick would.
Okay.
Because, I mean, they're just observing it. It's not what actually is happening.
Okay.
So maybe it'll actually be a 10-foot pole. It'll actually be a 5-foot pole.
Okay.
Since it won't fit.
Okay. So let me think. Let's say this. The way Mr. Nappy is going to prove that he wins the bet is when he tells Mr. Chernick, when I get to the middle of the barn, I want you to take both doors of the barn. So right now the barn's open. And I want you to shut them at the same exact time. Instantaneously, shut the doors. And what he says is, if I can get through that barn, when you shut those doors, then I essentially fit inside the barn. Okay? So I want you to think about that. So it's an instantaneous shut. It's let's say he's running, and then once he's in the middle, the door is instantly shut and come back up. And then he continues running. Take time to think about it. You guys can talk about it amongst yourselves. So that's what we're going to judge as fits in the barn, if the doors can shut. Because if the pole is too big and it shuts out, and the door is shut, the pole is going to get caught in the door. But if the barn is able to shut both doors, the pole is essentially fit inside it. Yeah. I'm asking you if that will happen. If Mr. Nappy can run, and when he gets to the middle of the barn, both doors shut.
I'm picturing
And then he continues.
like actual Nappy and Chernick doing this together. It's really funny.
Does he get through?
Imagine Nappy just running with a pole into a barn. Yeah.
87%.
I'll give you a hint.
It's funny.
You watched that simultaneity video before? Use the concepts from that simultaneity video and apply it to this problem. You know the answer, right? I think so. You know the answer?
Yeah.
I like your hint about this time.
Yeah.
I mean, yeah.
We got pushed.
It's relativity. You can't just say actual.
So we've looked at how
That's the whole point.
distance has changed, but what if time has changed from one reference to two? Think about that. Give you guys 30 more seconds.
Yeah. We lay on the floor.
Okay, let's take a vote.
Wait, would it matter when Mr. Chernick's
Let's just say he's a stationary observer watching the event take place. So, who thinks that Mr. Nappy's going to win the bet, and Mr. Chernick's going to see a 5-meter pole fit inside of a 5-meter pole? See some timid hand raised.
If the ball is 5 meters and the pole is 5 meters.
Let's say it's a perfect fit, so he said they can. So we got a few hands. Who thinks Mr. Chernick's going to win the bet, and Mr. Nappy will see a 2.5 meter barn, and the pole not fit in the barn? Okay, so about, I say 2/3 of you raise your hand at one point. So here's the thing. You're all correct and you're all wrong. Both of them are actually correct, and I'll explain to you how this paradox is resolved. So we talked about the simultaneity of time. So we have two different events. Let's treat them differently. And we'll treat them in both reference frames. We have the back door closing, and we have the front door closing. So, in the stationary frame, Mr. Chernick, just like the lightning bolts from the guy who's not on the train track, he's going to see the front door event, the door closing, and the back door event, the back door closing, happen simultaneously, meaning at the same exact time. But remember the person who was on the train? He saw the lightning bolt in front of him first, and then he saw the lightning bolt behind him as he was moving. So what Mr. Nappy sees is he sees the back door close first. Then at a later time in his reference frame, the front door closes. So what happens is this, and I'll show you a picture to best describe it. So this is going to be what Mr. Nappy sees, what Mr. Chernick sees, I'm sorry. So Mr. Chernick is watching a ladder pole, a moving, let's keep calling it a pole, a moving pole at a stationary barn. So Mr. Nappy runs into the barn. When he gets inside, both doors shut simultaneously. Then both doors open up for him, and he continues through the barn. He fits. So the pole does not get destroyed. But let's look at it from Mr. Nappy's frame of reference. So he's standing still. The barn is moving towards him, a shortened barn. So what he sees is he's standing still. That's why the ladder is in the same column at all times. A small barn is coming towards him. But the front door closes first, then opens up. He continues running. And at a later point in time, the back door closes. And the barn continues going. So whether or not the barn fits inside, whether or not the pole fits inside the barn, you guys can determine who wins the bet. It doesn't really matter. But the point is the pole does get through. And both reference frames will observe the same thing happening in terms of the same event. And it's not like in one reference frame the pole gets destroyed, in another reference frame the pole gets through. They'll both see the same things, but they'll observe it at different points in time and different points in space because they've adjusted their coordinates. Nice. Yes, question. Okay.
Are you saying when if that happens?
So this goes back to Einstein's postulates. He's saying that the laws of physics are the same in all reference frames, inertial reference frames. So they're both in an inertial reference frame. So whatever they observe is what's actually happening. But it's what's happening in terms of their coordinate system, which is essentially their reference frame. So events in one person's reference frame, this is the kind of the key of relativity. Events in one person's reference frame could be separated by a certain distance at a certain time. But in a different reference frame, they're separated by a different distance at a different time. They don't have to be the same. And that's what's different about relativity and classical mechanics. In classical mechanics, there is one time. Either they happen simultaneously or they don't. What relativity teaches us is because of the finite speed of light, some of the things that are simultaneous aren't in a different reference. Any other questions? Yeah.
What happens if you take the back door and just close it?
Back door close it?
Yeah.
Okay, that's a good question. So one other thing in relativity that you have to accept is there's no such thing as a rigid object because information can only travel at the speed of light. So what would essentially happen is let's say the back door shut and stayed shut, right? So let's talk about which we're going to talk about first. Let's talk about Mr. Nappy's frame. That's the more interesting one. So he's running with his 10-foot pole, a 10-meter pole, and he hits the back of this barn. That's only 2.5 meters. But when that back door closes, it stays closed, right? So you think something's got to give. He's stuck. But the information that the front of the pole got stuck against the back door hasn't reached the back of the pole yet, because information travels at the speed of light. So that back of the pole will continue moving, because it doesn't know that it got stuck. Eventually the information reaches, and then you have the pole breaking or something along those lines. But the back of the pole will continue moving until a point where the pole breaks because of stress-related forces, which would have happened anyway if the pole hit the back of the barn.
But it wouldn't
yeah,
be inside the barn, right? The back end of the pole would.
So the idea is that the back end of the pole would end up meeting up with the information that it hit the front end at some point. We can calculate it. It wouldn't take that long. It would honestly just be, we'd say this, the information travels back at the speed of light, and we have the back of the pole traveling at 0.866 c. So they're going to meet somewhere in the middle, and the pole will continue moving until the information reaches it. Okay, so Mr. Cherney's reference frame. So he sees the shortened pole hitting the back of the barn. Let's see. Okay, so it's not going to get shorter. It's a good question. All right. The issue I'm thinking we're running into is, remember, inertial reference frames means no acceleration. So stopping the pole is essentially introducing an acceleration. So things get tricky when you introduce accelerations. Although there probably is an explanation, and you can probably find it online. Google pole in the barn paradox, and if you guys are interested, and you'll find like this Wikipedia article that has these pictures. You'll find plenty of material on it. More questions?
Weird paradoxes. I remember when I took this course, it was about jousting, like people running at each other with different relative speeds and observers. Did I show that in class?
Yeah, you showed the last.
It's crazy, yeah. And who dies? Who wins the joust?
Yeah.
What the observer sees, and it gets insane. Yeah, so
Yeah, there are some crazy paradoxes. I think another one that's really interesting, which is very similar. Put a bug in a hole. So let's say this is a little spider. And let's say we have a screw that's going into the hole. So let's say in the screw's reference frame, let's say it's a very similar setup like this. The depth of the hole is going to shrink, because the hole is moving at it, let's say at some large speed. So it's going to squash that bug. But in the bug's reference frame, the screw is going to get shortened because the screw is moving, and it's not long enough to squash it. So does the bug get squashed? It either happens or it doesn't. And we could also investigate that paradox. And that's kind of what you were talking about with the pole having to extend or not, because just like when this screw reaches the edge of the hole, the information that it stopped hasn't reached the front of the screw yet. So it might continue moving for a little bit. You can do some calculations and figure out whether or not it squashes the bug.
So macroscopic things like bugs and screws and stuff, it's hard to sort of imagine how this really works. For me, anyway. But you know, Adam pointed out before, in the worlds of particle physics and you know, accelerators and things of that nature, you look at the LHC, this stuff is used every day. I mean, with subatomic particles, this is real. We observe this stuff more or less directly.
All right, I want to talk about this this paradox a little bit more. This might help answer our pole in the barn question. So, and again, it has to do with simultaneity of time. Let's see. So this would be. So these are the two situations I guess we're looking at. This is from the frame of reference of the bug. He sees a short screw. So he'll see, let's say that in the end of the story, the bolt does squash the bug. What the bug will see is that the edge of the screw will hit this first, and then elongate and squash the bug. While the bug will see him get, well, there are two events. Let's say the bug is an observer that lives past death. He'll see the screw hit first, and then later, because information that the screw has hit the bug hasn't reached the top of the screw, the edge of the screw will hit the part of the ground. So that's kind of like the same situation we found before. Yes, question about
I'm not sure if this is the same exact, but it's sort of like a Heisenberg principle.
Say that again?
The Heisenberg principle where like you throw like there's a cat in the bunker and you throw something.
Yeah. It's the Heisenberg principle. Okay, so the Heisenberg uncertainty principle is a concept that's usually used within quantum mechanics, and what it tells you is that if you know the position of a particle, you can't know for sure its velocity, and if you know its velocity for sure, you can't know its position. So there's a certain amount of uncertainty that's built into every system. This doesn't correlate exactly because these are certain events. These events are happening, but they're just happening at different times and different positions within each target. Don't worry about that. Uncertainty principle is a very interesting topic. I could have done a lecture on that. I was actually thinking about doing data relativity, but I figured this correlated with what you guys are learning a little bit more because there's velocity and distance in the object. So. Right, correct. That's the biggest point to make about relativity. There is no absolute reality. There is no absolute time, and there is no absolute displacement. That's essentially what distance is. So in different reference frame, we measure different. You'll measure different criteria, but they're both equally valid in any reference, in any inertial reference frame. They're both reality for that reference. Then he will not get squashed the other. The math will add up so that. And then, yeah. It's not like one reality the bug gets squashed, and in one reality the bug doesn't get squashed. What I was explaining was the time at which the bugs get squashed might change within each reference frame. That's what I was suggesting when I drew these pictures. So one of the event of this, of the edge hitting the floor and the screw hitting the bug, the events might have flipped which one happened first, depending on the
So because this is like, special relativity has to do when you're moving close to the speed of light. So at the end of this paradox, you have two objects that are touching, not moving. So the bug will get squashed because special relativity doesn't exist when the screw starts to slow down. Like it will decelerate to zero when it hits something.
Yeah. So
it will eventually squash that bug at a different time, but special relativity is still.
Again, the exact mechanics of the system we can't really think about right now because I haven't introduced general relativity, which has to do with accelerations. So we're talking about things that are accelerating right now. But the concepts that the Lorentz transformation